Hi, in this video I'm solving this problem from the International Math Olympiad of this year. Now to be honest, usually I cannot solve IMO problems. When I was in high school, I was national champion in a different subject, but for math, I didn't make the national team. As a matter of fact, I never made it to even close to the national team. I always get eliminated 2 or 3 or maybe in 4 rounds outside the national team. So yeah, usually IMO problems are not something I can solve. So when I was able to solve this one, I was thrilled. I posted my solution to the author problem solving website and nobody said anything, so I assume it's right. Because trust me, that website is full of IMO level people, and if there's a mistake or if there's a wrong answer, they will let you know. So let's go. All right, the question. Let R plus denote the set of positive real numbers. Find all functions from R plus to R plus such that for each x in R plus, there is exactly one y in R plus satisfying that inequality xfy plus yfx less than or equal to 2. Always start out strategizing or doing some scratch paperwork. The first thing you notice is that this inequality here, let's call it star, is symmetric in terms of x and y. You switch places of x and y, then that inequality is still true. So that means that if y is the unique number that goes with x, then that also means x is the unique number that goes with y. The x and y are unique pairs. An inequality like this, especially with a plus sign right here, and or for that matter, number 2 right there, calls for the AMGM inequality. The AMGM inequality says the arithmetic mean is always greater than or equal to the geometric mean. That a plus b over 2 is always greater than or equal to square root of ab. Well, this one has the inequality the wrong way around, which sort of suggests that it really should be an equal sign. The less than part is probably a red herring. So we should aim for an equal sign, which happens when a equals b. xfy is equal to yfx. And once I'm here, I was thinking, well, wait, what if it's even simpler than that? What if x and y are just equal to each other? What if I just have x here? Then yeah, definitely I have the inequality. Definitely I'll have this condition. And now that I think about it, those of you who have done a lot of work with AMGM, you're probably familiar with this inequality. X over y plus y over x is always greater than or equal to 2. So that sort of suggests that f of y is equal to 1 over y, and f over here, and f of x is equal to 1 over x. So the strategy will now consist of 2 things. First of all, I'm going to prove that y equals x. And then second, I'm going to prove that f of x equal to 1 over x. So that's my goal. So what I did was I played around with AMGM a lot. I derived a lot of properties of f. For example, I sort of figured out that f is decreasing. But they're not helpful. They're consistent with my guess that fx is 1 over x, that they're not helpful until out of nowhere, I sort of hit upon like a big light bulb, and we'll see it when we got there. So now that I have my strategy, let's do the proof. My claim 1 is that y is equal to x. So let's do some definition first. X star denote the y that's in this problem. the unique y that satisfies the star inequality. So since star is symmetric, that means that if y is equal to x star, then x is y star. So this relationship comes in unique pairs. Claim. Claim is that x star is equal to x. The proof will be by contradiction. Suppose x star is not x. Then that means if I insert an x in here, the inequality will not work, right? Because y is a unique number. The x star is unique. So if I plug in x and x, the inequality will be false. That means x of x plus plug in x for the y times fx is not going to be less than or equal to 2. It's going to be greater than 2. That means x of x is going to be greater than 1. And also because of the symmetry, if I plug in y and y, the inequality star is false. So that means y of y is also going to be greater than 1. This one means fx is greater than 1 over x. And this one means fy is greater than 1 over y. So now what happens if I do x fy plus y of x? X is equal to x. Fy is greater than 1 over y. So it's greater than 1 over y. Plus y, and fx is greater than 1 over x, so it's greater. Which is equal to x over y plus y over x. And by the AMGM, x over y plus y over x is going to be greater than, I'm going to put greater than equal to for now, but I'm going to go back and erase that. Greater than equal to square root of x over y times y over x times 2. Like this. Cancel, 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 cancel. So this just 1. So that means x over y plus y over x is greater than equal to 2 with equal if and only if x equal to y. But we assumed that x is not equal to y by our contradiction. We assume that x is not equal to y. So therefore, the whole x fy plus y fx is greater than this stuff, and this stuff is greater than 2. So that means this expression is greater than 2. But that's no good, because that contradicts our assumption. Our definition up here is that we let y be the x star. And if y equals to x star, then this expression is supposed to be less than or equal to 2, not greater than. So we have our contradiction, and therefore we have the proof of the claim. QED that x is equal to x star. For all x. Now that we have our claim, we're going to use it to prove that fx is 1 over x. Let me put the expression over here so we can remember what it is. X fy. This is the star inequality. Okay, so if x and x star are the same thing, that means if we plug x in for y into the star, we should get true. We plug x and x into the star, it should be true. X of x plus x of x less than or equal to 2. This is 2 times x of x. We divide by 2x both sides. So we should get fx is less than or equal to 1 over x for all x. We're able to do all these inequality manipulation without worrying is because the question says all the numbers are positive. All the numbers are positive reals. X is positive, fx is positive, everything is positive. So we can work with these inequalities without worrying about the direction of the inequality. All right, so we got to an inequality that says things are less than or equal to. We're going to prove that it's actually equal to, so it's not going to be less than at any point. This statement is true for all x. Now comes my big light bulb moment. I have the expression fx, xfy plus yfx. And I sort of want this one to be 1 over y, and I want this one to be 1 over x. I already forced this to be x. So I want to concentrate on forcing that number to be 1. So I'm going to define that number. For each x, let's C equal to basically that number there, x of x. Therefore, I have f of x is equal to C over x. And therefore, C is less than or equal to 1. By the way, this C is not unique for all x's. It's a different C for each different x. So I'm not even saying that fx is of this form for all x's yet. Not yet. It's just like one C at a time. So in your head, you might think in terms of like a C naught and an X naught or something. Okay? It's a different C for each x. So now I'm going to compute that expression x times f of y plus y times f of x. And I sort of want this one to be 1 over x. So I'm going to flip it over and I put x over c in here. What is this equal to? Well, first of all, this is c over x. So the x's cancel, the c's cancel. Now, what about this f? Well, we have this. We have that f of x is less than or equal to its reciprocal for all x. So that's definitely going to be true for x over c. So this is less than or equal to. And the x's cancel. And what do we know about c? We know that c is less than or equal to 1. So this whole thing is less than or equal to 1 plus 1, which is 2. Oh, look, that means that the x over c satisfies the original star inequality. X over c is x star. But we already know that x star is x. And therefore, c is equal to 1. And that means fx is equal to 1 over x for each x. Done QED. Well, that's been fun. I hope you had fun too. Like, share, and subscribe for more contents. And thanks for watching. Bye.